Okay, welcome back. Part 2 of lecture 13 here. We're going to talk about ozonolysis of alkenes. Right. And the ozonolysis reaction has two flavors associated with it. And they are different in terms of the second step of the reaction. So we call them an oxidative or reductive ozonolysis. And so I'll first talk about the reductive process, then we'll talk about the oxidative, and then we'll try to bring them together. And again, this like hydroboration, this is going to be a newer type of transformation. The mechanism is sort of unique in that there aren't going to be a lot of other reactions that share the same mechanism. And so you'll have to spend some time really trying to understand it. But it's an incredibly powerful reaction. We use this, we do ozonolysis constantly in the laboratory. And so it's a good one to know. So, all right, we'll start with the reductive process. And the general reaction is as follows. So I'm going to take some sort of alkene. And I'm going to first treat that with ozone, which is O3. And then in a second step, I'm going to react that with some sort of mild reductant. And one that's commonly used is dimethyl sulfide. So okay. And literally what's going to happen here is the alkene is going to be clipped down the middle, and each carbon of the alkene is now going to be double bonded to oxygen. So we can label them if that's helpful. So A and B, A and B. Okay. All right. So what's the mechanism? As I said, the mechanism is complicated. It's a two-step process. So we'll first go through step one. Okay. So I've drawn the alkene plus the structure of ozone. So ozone has a very unusual structure. You've got 3 oxygens in a row, and it has it's zwitterionic, so you have these internal charges. What's going to happen is this is going to do what's known as a 3+2 cycloaddition with the alkene. Okay, useful to know the name. It's not that important to remember. The way it works is we take a lone pair on the oxygen that's negatively charged, push them to one of the carbons on the alkene. We then take the electrons in the pi bond, push them to the terminal oxygen, and then take the electrons in the OO pi bond and push them towards the central oxygen. And if you work through this correctly, what you should end up with is a molecule that has no formal charges. All the oxygens now have their usual 2 bonds. and it looks like that. All right. And so this intermediate is what's known as a malosonide. Stable at low temperature. Okay. But you've got an OOO linkage, and I just told you that the OO bond in hydrogen peroxide is very weak, about 36 kcals per mole. The bonds are even weaker here. And so if you warm up the malosonide, it does an interesting fragmentation reaction. And so to show that, we're going to take the electrons in the central carbon-carbon bond and have them move over to the oxygen on the left. We then need to break the OO bond so we don't violate the octet. So I'm going to take those electrons and just push them up to that terminal oxygen. And then this oxygen on the right has 2 lone pairs, and I can take one of those lone pairs and push them down. And so what I end up with is two molecules now. Okay. And the molecule on the left is known as an aldehyde. The one on the right, we're back to an unusual structure. This is a carbonyl oxide. Okay. And those two things are going to recombine in a different fashion. So to show that, I'll first redraw them on the next slide. Okay, so I've redrawn them exactly as they were on the last slide. We're going to flip the aldehyde over. So okay, and now what I can do is have that terminal oxygen that's negatively charged attack the aldehyde carbon, and then I'm going to take those electrons in the CO pi bond, bring them up, and have them attack the carbon of the carbonyl oxide, and then take the electrons in the CO pi bond there and push them up to neutralize that formal positive charge. And so what we end up with then is this type of structure. And this is an ozonide. Okay. So in the first step of an ozonolysis, you've got your alkene in solution, typically at about minus 78 degrees Celsius. And then O3 is a gas, so you bubble it through the reaction. You get this cycloaddition to form the malosonide, fragmentation, and recombination to make the ozonide. And then then you have a solution of that ozonide for the second step. So in step 2, then you add your dimethyl sulfide. Okay. And the key to understanding the transformation here is going to be to remember 2 things. One is that in my ozonide, I've got an OO bond again, very weak, 30 to 40 kcals per mole. And then also sulfur is a relatively, is a modest reductant. It easily will donate its lone pairs of an electrons to an electrophile. And so there's a reaction that occurs between the ozonide and the dimethyl sulfide. And so to show that, I'll start with my lone pair on sulfur, have them attack. Oops. Draw an arrow to one of the oxygens. Okay. And then break the OO bond, have those electrons come down towards carbon. Can't violate the octet rule, so I need to break the CO bond, and I'll have those electrons just come down and end up on that oxygen. Okay. And so the immediate product of that interaction then is going to be my aldehyde. And sort of an unusual looking species. Okay, like that. And then that compound on the right itself is not stable. So there's a fragmentation that occurs where I take a lone pair on oxygen, push it down, and then break the CO bond, pushing electrons onto the oxygen. And what I end up with then is my ketone. Plus, some of you may recognize this molecule. This is dimethyl sulfoxide. DMSO, okay? And then I'm done. So I've got my aldehyde, I've got my ketone. The two carbons here were the carbons that were in the alkene starting material, okay? And so then I just want to talk about the oxidative process. And so the oxidative process is different in its outcome when you have one substituent and one hydrogen at on one of your alkene carbons. And so we'll draw the same. We'll start by drawing the exact same alkene. So and now to do the oxidative process, the first step's identical. We'll treat with ozone. Second step, though, I'm going to treat with water and hydrogen peroxide. Okay. And the products that I get out are going to be a carboxylic acid and a ketone. Again, it might be useful to label the carbons in the alkene. So A and B, A and B. Okay. And so how does this reaction occur? So the first step is the same. So we won't go through that again. You form that ozonide in solution. Step two, of course, is what is different. Okay. And so I'm going to have my ozonide. I'll just start from there. And we're going to treat this compound with water and hydrogen peroxide. And so the first step is actually, in terms of the flow of electrons is the same as the reductive process. The water is going to attack one of those oxygens in the ozonide. So I'll take a lone pair and have them come over and then break the OO bond, push those electrons down between carbon and oxygen, and then break this CO bond. And so what I end up with is an aldehyde from the left-hand carbon, and then a very unusual species. And I don't think that your book actually goes through this mechanism in detail because it is a bit complicated. But you get to a structure like this. Put in the lone pairs there. And that is going to collapse. And so one of the lone pairs on this negatively charged oxygen are going to get pushed down to carbon. And then this group that's attached is going to leave. So I cleave the CO bond. And so what I get then is the ketone plus O minus OHH plus, and then you can invoke, just to make it complete, we can invoke a proton transfer to get to hydrogen peroxide. Okay. And so the key point is that the aldehyde intermediate that you form is not stable in the presence of hydrogen peroxide. And so the hydrogen peroxide is going to attack the aldehyde at the carbonyl carbon. Okay. And again, I need to break the CO pi bond so I don't violate the octet rule. So I'll push the electrons up to oxygen. And what I end up with is a tetrahedral intermediate. Like that. Okay. And then there's a sort of a collapse of the intermediates that occurs. And so there are different ways to draw this. The way I'm going to draw it is I'm going to take this negative charge on my oxygen and have it attack this proton here, and then push these electrons down and cleave the OO bond. Okay. And we'll redraw the immediate products over here. So we've got from the carbonyl, we've got O, H, H, CH3. Okay. Sorry, this is OH. And then I've got hydroxide. That was my leaving group. And then finally, I'll draw it on the next page. There's an acid-base reaction that occurs where I transfer a proton to get me to water plus my carboxylic acid. Okay. And so the key point is that in the oxidative process, the aldehyde intermediate is unstable towards further reaction with hydrogen peroxide. The ketones that we form, because they don't have an adjacent proton, are stable. So ketones do not react further. Okay, so for example, they can undergo nucleophilic attack by hydrogen peroxide. But the intermediate that you form doesn't have an adjacent proton. So if you allow me just to go back one slide to remind you what's happening. Where was it? What happened here? For some reason, I seem to have lost. All right, I seem to have lost that last slide. That's bizarre. All right, but let me redraw it from an aldehyde. This you'll have them right on the same slide for comparison. Okay, so this, I'm just redrawing what I had previously showed you because I seem to have lost the last slide on the iPad here. So previously we said that the peroxide attacks the aldehyde and you form this type of intermediate. Okay, and then for the aldehyde, there was a proton transfer that occurs where I pick up that proton on the oxygen that's negative charged, push electrons down, and kick out hydroxide. And so I wind up with the protonated carboxylic acid plus hydroxide. The key step is this proton transfer here, and you can see that when I do this on a ketone, there's no proton to abstract. So the ketone can undergo 1,2 addition, and it certainly does, but there's nothing else for it to do. And so once you form that tetrahedral intermediate, it just reverses. And so the bottom line is that ketones do not react further. Okay. And so the final bit I want to say is that it's important to know that these differences in outcome. And so the differences arise from the oxidative or reductive conditions that you employ and the substitution pattern on the alkene. And we can draw a very simple table to describe that. So if I have an alkene carbon bearing 1 hydrogen, okay, and then I do my reductive workup, I end up with an aldehyde from that carbon, or from that alkene, that end of the alkene. Okay. If I instead do an oxidative workup, I get to a carboxylic acid. Okay, and so that's the one that you need to sort of keep track of. The alternate substitution pattern, when you have 2 carbon atoms on the alkene carbon, the reductive workup always gives you a ketone, and the oxidative workup always gives you a ketone. So that one is easier to keep track of. Okay, it's just when you have a hydrogen on one of those alkene carbons that you need to pay attention to what your workup conditions are. So, all right, so this lecture had 2 new reactions: hydroboration oxidation, then oxidative cleavage, followed by reductive or oxidative workup. The mechanisms of those transformations are distinct from anything that we've learned, and I've told you the best way to get your head around this material is to learn mechanism. And so you really should anticipate that you'll need to spend a bit of time on this content to become comfortable with these mechanisms, but it'll be time well spent because these are very useful transformations that we'll use throughout this semester and then the following. Okay, and of course, as always, if any questions come up, you can email me or the TFs and we can help you to work through anything that you don't understand. All right, so that's all I want to say. Thanks and take care.